Hey everybody, Dr. A here, and in this video we are going to be exploring another example of combined loading. So given to us, we're being asked to draw the normal stress distribution in the cross section due to the eccentric column load. So here we're given two figures to help us visualize what we're looking at. So in the left figure, we have a two-dimensional side view of this column, and we see that it is supporting a 2-kip vertical load that is offset with an eccentricity of 6 inches away from the center line of the column. This symbol right here is a C and an L that means center line. We see that the whole column width is 24 inches. So the center line is passing through the 12-inch center line markers. So on the right side, we have that same column, but in 3 dimensions. So the 24-inch dimension is shown here, and that's the same 24 inches that we see down here as 12 inches and 12 inches. At the top of the column, we have sketched on here a y-axis for the cross-section and an x-axis for the cross-section. In the direction of the y-axis, we have a dimension line of 18 inches. So we see that this 2 kips is lying along the x-axis. It's on the x-axis. It's just a distance of 6 inches away from the center line of the column. So if we want to, we can note that this distance right here from the center of the column to where the 2 kips is, that's the 6 inches that we see in the two-dimensional figure. So when we draw this stress distribution, we're actually going to draw it in the 2D figure just because that's going to be a little bit easier and quicker to draw and for us to visualize. But it could be extended into 3D through the 18-inch dimension if we wanted to. But we're just going to draw it in 2D when we get to that point. So let's go ahead and get started. So under solution, the first thing we need to notice is that, again, that 2 kips is offset from the center line with a 6-inch eccentricity. So what I'm going to do is I'm going to draw a free body diagram with a cut section in the column, okay? So here I'm going to redraw part of my column, and I am going to draw a cut section in somewhere in the column, okay? And then I'm going to go ahead and resketch the center line here. There's my center line. And then the 2 kips is 6 inches away from that center line. Now, the next thing that's going to show up here is going to be an internal normal force, which I'm going to call N, and an internal bending moment that I'm going to call M. Now, how do I know there's going to be an internal normal force and an internal bending moment? Well, the applied load of 2 kips is normal to the section. So you know you're going to have a normal force develop. What about this bending moment? Well, because that 2 kips is at an eccentric distance of 6 inches away from the center line, it's going to cause this column to tend to bend or want to rotate. And what will resist that is an internal bending moment that will develop in the cross section due to that offset load. Now, there's not going to be a shear force develop. I mean, if you wanted to, you could draw a little V for shear force there, but it will be 0. So let's go ahead and apply some equilibrium equations. We're going to say sum of the forces in the y direction equals 0. And from this simple equilibrium equation, we can clearly see that the normal force is just going to be 2 kips in compression or pointing into the cut. Next, I'm going to say sum of the moments about the cut equals 0, taking rotations counterclockwise as positive. And then in this equilibrium equation, I'm going to have that internal bending moment M, and then I'm going to have minus 2 kips times 6 inches equals 0. So I'm going to take the bending moment not only at the cut section, but it's actually like about the center line. So the perpendicular distance that I'm measuring from the applied 2 kips is the 6 inches away from the center line, because the center line also represents the centroid of that column. So doing some rearranging, M is going to be equal to 12 kip inches, and that's going to show up as a counterclockwise bending moment at the section. So that's just simple method of sections, nothing really fancy about that. Now what we need to do is get the stresses that are developing in the section due to the normal force and the bending moment at the cut section. So how do we do that? Well, we need to remember that average normal stress, sigma, is going to be force divided by cross-section area, N over A. So what we have here is the cross-section dimensions. We know that the cross-section area is going to be 24 inches by 18 inches. So we can go ahead and substitute values in here. We're going to say this equals 2 kips, or I'm going to go ahead and put it as 2,000 pounds divided by 24 inches times 18 inches. And so that average normal stress is going to come out to be 4.63 PSI in compression. Now I'm going to call this sigma sub n just to make sure I know that this is the normal stress due to the normal force in directed as an axial force, okay? Next, I'm going to calculate the flexural stresses, okay? So I'm going to call this next couple of stresses sigma sub f for flexural stresses, all right? And that's going to equal m times a centroidal distance divided by a moment of inertia value. So it's going to be m times something divided by something. Now, what are those somethings? Well, before I write them down, let's go back and look at our original figure. Notice that in the 3D figure, we can see it pretty clearly. This 2 kips is causing a tendency of rotation about the y-axis here, okay? It's causing a tendency, think about it, a tendency of rotation about the y-axis. That's because the 6-inch perpendicular distance is a perpendicular distance away from the y-axis, even though it's along the x-axis, but the tendency of rotation is about the y-axis. Because it's about the y-axis, the section properties I'm going to need are actually going to be x bar, which is 12 inches, and I'm going to need I sub y, the moment of inertia about the centroidal y-axis, because I have bending about the y-axis in this figure. So down here in my governing equation, I'm going to say that that's m times x bar over I sub y, okay? Now we need to calculate these values. So x bar is our 12 inches. We see that that is the distance from the center line of the column to the edge of the column in the x direction. If you're having trouble visualizing this, pause this, rewind the video, and rewatch it so you can convince yourself of it. The moment of inertia about the centroidal y-axis is going to be hb cubed over 12, okay? So h is the dimension of the column in the y direction. That's the 18 inches. And then b is 24 inches cubed, and then over 12. So I sub y is going to be a value of 20,736 inches to the fourth. So I'm going to substitute all my values in here, and I'm going to get the flexural stress as equal to 6.944 PSI. And on one side, it's going to be in tension. On the other side, it's going to be compression. So how do I know which is which? Well, you just look at your original free body diagram. This region on the left side of this 2D drawing is going to be experiencing a tensile flexural stress, and the region on the right of the center line is going to be experiencing a compressive flexural stress. So I'm going to go ahead and write 6.944 PSI, and on the left side it's in tension, on the right side it's in compression. So the best way to show this visually is to just draw it out. So I'm going to go ahead and redraw a new figure here, and we're going to draw that center line right down the middle with our 2 kips here. 6 inches here, and there's our cut section. So I'll go ahead and I'll show the compressive normal stress distribution here, and that's a uniform stress distribution, and that is the 4.63 psi in compression. And then superimposed on top of that is the flexural stress distribution. So coming off on the right side, we have an additional compressive sense here. So this value is the 6.944 psi in compression. And then on the right side, we're going to have that same magnitude of stress, 6.944 psi, but that's in tension. And so both of these sets of stresses are normal stresses. One of them is due directly to the normal force, and the other is due to the flexural sense, the bending moment causing a normal stress distribution. Because they are both normal stress distributions, it's all perpendicular to the cross section, we can superimpose, use the principle of superposition to add these two stresses together. And so what kind of stress distribution what's it going to look like basically whenever we superimpose these together? Well, let's redraw our figure yet again. The best way to help visualize these things is just keep redrawing it until you can see it clearly. Okay, so there's the 2,000 pounds. I'll draw that as pounds this time instead of kips. And there's the cut section. So what is this stress distribution going to look like? Well, we're going to add directly together the two compressive stresses. They're pointing in the same direction. It's an entire compressive zone over here. And so when I add these together, I'm going to get a compressive stress of 11.57 psi in compression on the right side. Now on the left side, you notice that these stresses are pointing in the opposite direction. So my 4.63 psi needs to still be in compression over here on the left side, but the 6.944 psi is in tension. So one of them has to be positive, the other has to be negative. In either case, you have a net tensile effect here. So we'll make a note here. We have a net tension on the left side. And so when you superimpose these together, you're going to end up with a value of 2.31 psi in tension. So I'm going to draw that pointing away from the surface there. And then we can connect these two vectors. If you draw it to scale, it'll look a little bit better. So we're going to connect these together, but not directly, because notice the left side's in tension. So we're going to see that we're going to look something like this. Draw that a little bit better. Here we go. And so we see that the center of the stress distribution is going to move a little bit to the left. You could calculate that if you want, but it's going to move a little bit to the left. The problem didn't actually ask us to calculate these distances, but you could use some simple geometry and calculate that. So this is going to be our overall did not mean to erase that. This is going to be our overall final solution here, where we have 2.31 psi in tension on the left and 11.57 psi in compression on the right. Notice the direction that these stresses are pointing with respect to the cross section. Compression is pointing into the cross section and tension is pointing out of the cross section. So that's going to conclude this video. If you found this helpful, please hit like and subscribe.